So that's an example of two very commonly used method of estimation, and we'll cover a different method in the next lecture. Now, there are often multiple alternative estimators we can use to estimate a given parameter. And the question is which one is best. And in order to be able to determine the best estimator to use in any given situation, we've got to find ways of evaluating different estimators. And in statistics, we try and do this systematically and quantitatively. So as explained above, an estimator is a random quantity with an associated sampling distribution. And what we're going to do actually is we're going to use the characteristics of this sampling distribution to assess the quality of estimators. But before we go on to do that, we're going to ask ourselves a simple question. If we do want to evaluate an estimator, what properties do we think would be desirable in the estimator's sampling distribution? And typically we talk about three properties. Bias, variance and mean squared error, and these first two properties are finite sample properties. And thirdly, we talk about consistency. So properties 1 and 2 are referred to as the finite sample properties of an estimator, while property 3 is an asymptotic property. And I'll go through these now, and we'll then look at, again, some concrete examples of what these mean in practice. Okay, so first, the finite sample properties. And we'll start with bias. Now, the bias of an estimator, W, is defined by this expression here. It's the difference between the expected value of the estimator minus the true value of the parameter. And an estimator is said to be unbiased for parameter theta if the expected value of the estimator is equal to the true value of the parameter that we're trying to estimate. So that is, the expected value of the estimator's sampling distribution is equal to the value of the parameter to be estimated. So that sounds like a very obvious property. In expectation, we want the estimator to correspond, or in expectation we want the estimator to correspond with the true value of the parameter we're trying to estimate. We don't want it to give us an expected value that's somehow different than the parameter estimate. If it does, that would be said to be a biased estimator. Secondly, and again, remember these properties are being discussed in relation to the sampling distribution of the estimator. The variance of an estimator at its sampling distribution is given by this expression here. So the variance of W is equal to the expected value of W minus the expected value of W squared, right? So that's just the expression for variance. You've seen that before. An estimator is said to be more efficient than any other estimator. So W1, estimator W1 is more efficient than any other estimator W2 if it has smaller variance, okay? And efficiency is therefore a relative concept. But efficiency is desirable. We want the variance of our estimators to be as small as possible, or in other words, we want our estimators to have a reasonably high degree of precision. So that's the first two properties, and we'll look in a minute at what they mean in practice, as I said. But note that, just one thing to note, the expectation and the variances here are taken over theta. But that's because the properties of bias and efficiency must hold for all values of theta that we want to consider. Okay, so we might desire an estimator that is unbiased and low variance. That's what you might imagine from the conditions that we've just described, and of course often we do. However, there is often a trade-off between bias and variance, and so these two criteria are sometimes jointly evaluated via mean squared error. So I'll just introduce this concept. The mean squared error of an estimator W for some parameter theta is the function of theta defined by this expression here. That is, it's the average squared difference between the estimator and the parameter theta. And this average squared difference can be written in this form here. The mean squared error is equal to the variance of W plus the square of the bias. So that's quite useful because it combines bias and variance in a single quantity. And an estimator that has good mean squared error has small combined bias and variance. Note also that for an unbiased estimator, one where we can break this expression for the mean squared error down, the mean squared error will simply equal the variance of the estimator itself because it doesn't have any bias. The bias is 0. That is, mean squared error equals the variance of the estimator itself if the estimator is unbiased. Now, just building on this a little bit, we sometimes talk about what we call a best unbiased estimator. So if the estimator W star is unbiased, and if it has minimum variance in the class of unbiased estimators, that is, the variance of W star is at least as small as the variance of any other estimator we could look at for parameter theta, then that estimator is referred to as the best unbiased or the uniform minimum variance unbiased estimator. Okay, so again, that's bringing these concepts of unbiasedness and variance together, saying that the estimator is the best, the minimum variance unbiased estimator. Now that covers the finite sample properties. We're now going to talk a little bit about asymptotic results, which are concerned with the characteristics of the sampling distribution of the estimator as sample size tends towards infinity. So as sample size grows and grows and grows, what happens to the behaviour of the estimator? And when we're looking at those behaviour as n approaches infinity, we refer to that as asymptotics, the asymptotic properties concerned with behaviour as n grows and grows and grows. Before we look at the properties of estimator, we just have to define two important asymptotic results that we're going to use. Now, first is the concept of convergence and probability. And convergence and probability is concerned with how a sequence of random variables converges as the number of random variables we're considering increases, so as n approaches infinity. And a sequence of random variables is said to converge in probability to some random variable x if for every small number we can look at, in the limit, the probability of the absolute difference between xn minus x is less than that number, that limit, in the limit, that probability equals 1. And we write that convergence as the random variable xn converges in probability to x as n approaches infinity. So all convergence and probability really is saying is that as n approaches infinity, the probability of observing differences between xn and x becomes smaller and smaller and smaller. So it converges, this quantity here converges to this quantity here as n grows in size. The second asymptotic concept we're going to cover is convergence and distribution. This says that the sequence of random variables x1 up to xn converges in distribution to a random variable xn if in the limit the distribution, or the CDF of xn, is equal to the CDF of x. Such convergence in this case is written xn converges, not with p as in here, but with d, converges in distribution to the distribution of random variable x. And convergence in distribution is a weaker form of convergence than probability. We're not saying the random variables converge one to the other, we're saying the distribution of those variables converges as n approaches infinity, or as sample size grows. Think of it as sample size grows. And maybe these concepts will become slightly more intuitively obvious when we talk about two specific examples of them, or at least the first one. There are two particularly useful asymptotic results that concern sample means, and that's going to be important to us because often our estimators can be written as sample means. The first is called the weak law of large numbers, and what that says is that a sequence of IID random variables with expectation mu, and if we define the sample mean in the usual way as just the average, okay, the sample mean we've seen before, then for all of these numbers greater than 0, in the limit, the sample mean approximates or converges in probability to the population distribution, so the population mean or the expectation. So as the sample mean converges in probability to the expectation of the random variable or the population mean as sample size grows. And I'll show this in a minute, but it should be intuitively obvious. As we calculate an average from a sample, as that sample size grows in size, that average is going to get closer and closer and closer to the population average, because the sample is growing. We're covering more of the distribution in our sample as sample size grows. That's the intuition, really. The second theorem, the central limit theorem, is a theorem that is concerned with convergence and distribution. So let x1 to xn be IID random variables with expectation mu and variance sigma squared, both finite. Again, we're going to define the sample mean in the usual way. And then we're going to define a random variable z, which is the standardized sample mean. So sigma square root n times the sample mean minus mu over sigma. Then as n approaches infinity, this quantity Zn converges in distribution to a normal distribution with mean 0 and variance 1. And this central limit theorem is very important. What it's saying is essentially that the limiting distribution of a standardized sample mean is standard normal. And there's various different proofs of this concept. So we've got two results here. We've got the first, the law of large numbers, stating that as sample size increases, the sample mean converges in probability to the population mean, and the central limit theorem showing that the limiting distribution of a standardized sample mean is standard normal. And the reason why these results are useful is because many of our estimators can be expressed as these quantities, as averages, and therefore we can apply these two asymptotic laws to our estimates, or our estimators I should say. So let's just take these asymptotic results and come back to how we would use them to evaluate estimators. So the asymptotic property of estimators. First, we're going to talk about a consistent estimator. A sequence of estimators, Wn, indexed by n as a sample as x1 up to xn, indexed by sample size, are consistent estimators of parameter theta if their probability limit is equal to the true value of theta as n approaches infinity. So all we're saying is that as the sample size we use to construct our estimators increases, our estimator will converge in probability to the true value of the parameter theta. Okay. So by increasing sample size, a consistent estimator can be made to lie arbitrarily close to the true value of theta with probability arbitrarily close to 1. And a sufficient condition for consistency is that the bias and variance of the estimator both tend to 0 as sample size increases. Finally, in terms of the asymptotic properties of estimators, we're going to use the central limit theorem here and talk about an asymptotically normal estimator. So an estimator W is said to be asymptotically normal if the standardized estimator, that is square root of n times the estimator minus the parameter theta over the standard deviation of the sampling distribution, converges in distribution to a standard normal distribution. Okay, that's an asymptotically normal estimator. Okay, so quite a lot of material covered here actually. Convergence and distribution, I just want to summarize where some key points that I want you to take away from this. Convergence and distribution does not imply convergence of xn itself, but of the probability distribution associated with xn. It's thus a weaker mode of convergence than convergence and probability, and I said that earlier. Now, the property of consistency implies convergence in probability, while asymptotic normality implies convergence in distribution of the standardized estimator. So this is convergence in probability, this is convergence in distribution. And an estimator that is consistent and asymptotically normal is referred to as a CAN estimator. What I'm going to do now is use some examples to try and make this theory concrete, okay? Because I realise for some of you it might be new, and I think using specific examples can help us understand how it works. So what we're going to do is look at the simplest of all problems, in a way, the sample mean. So we have a random sample that are IID according to a normal distribution. And the sample mean, as we've seen, is both the method of moments and the MLE estimator of mu. Now, we can show analytically that the sample mean is an unbiased estimator of mu. And this is how we're going to do it. Remember, an unbiased estimator the expectation of that estimator's sampling distribution should be equal to the true value of the parameter we're trying to estimate. So we'll take the expectation of sample mean. That gives us this expression here. By the rules of expectation, this is a constant, of course, we can write this as this expression here. The expectation of random variable x is simply mu, but summing over mu gives us n mu. 1 over n times n mu gives us mu. So that's an analytical derivation to show that the sample mean is an unbiased estimator of mu. But we can also conduct a simulation looking at the sampling distribution of the sample mean to show some of the concepts that we've just described. And we're going to do this now in R. So here we have the R code. We've seen this before actually. We're going to conduct a simulation 1000 times in which we calculate a sample mean. We do it by taking 5 observations from a normal distribution with mean 10 and variance 4. And we save these values 1000 times, and this histogram here shows the results. We've plotted all of the estimates, we've plotted our 1000 estimates, which give us, if you like, an empirical representation of what the sampling distribution of our estimator, in this case the sample mean, would look like. And its mass is concentrated around the true value of the estimate, 10, but it has a distribution, as you can see, because it's a random variable. Okay. So the mean of our sampling distribution is 9.998. In fact, if we calculate it, and that's because, as we saw earlier, the sample mean is unbiased for mu, which in this case is equal to 10. Now we could use another. We could have used the median, which we're going to write as x tilde, to estimate the population mean, which actually is in fact also unbiased when the population is normal, and that's because the normal distribution is symmetric, so the mean coincides with the median. The mean of the simulated sampling distribution is 10.022, so again showing that it's unbiased. However, the sample mean is a more efficient estimator than the median, and that's because it's got smaller variance. So the variance of the sample mean for parameter mu is 0.76, which is less than the variance of the median for parameter mu, which is 1.46. And we could do this just by looking at the variance of the sampling distribution analytically for those particular estimators. Now, next, from the central limit theorem, we know that a mean, a sample mean, is a consistent estimator of population parameter mu. That's what the central limit theorem tells us. But we can also conduct a simulation to demonstrate this, and we're going to do this by generating a representation in R of the behaviour of the sample mean as n increases. So what we're going to do is we're going to calculate the sample mean for each value of n as n goes from 1 up to 10,000, and we're going to save the values we get and plot them. And that process produces the following plot, which is an example of the concept of consistency. So what it's showing is it's showing the change in the estimated value of the sample mean on the y-axis as n increases on the x-axis. So n is going from 1 up to 10,000, and these are the values that we get. And what you can see is that when n is small, values are much more erratic. Up here at 11.3, 11.4, whatever that is, a lot of quite erratic behaviour at the start. But as we start to get bigger in value, then it starts to tail off. And this is the property of consistency. So as the sample size is increasing, here we've got very small sample sizes, up here slightly bigger, and then up here very large. The behaviour of the sample mean as n is growing and growing indicates consistency for this parameter mu equals 10. And that's because of what we saw in the law of large numbers. So that's an empirical demonstration of the property of consistency. Okay, the final thing I want to talk about here is I want to give an example of bias. So we're going to talk here about the sample variance. Okay, so we've got our random sample. It's IID, normally distributed, mean mu, variance sigma squared. And as we've seen from above, the maximum likelihood estimator and the method of moments estimator of sigma squared is given by this expression here. That is in fact the expression you would use for the population variance. So we know in fact that that's a biased estimator, and the bias is equal to this term here. If you go back to, I think it was slide 9, we explained why that was a biased estimator of the variance when we do not know mu, when we have to calculate mu. Then we have to use 1 over n minus 1, which is why we get this bias here. So we're going to simulate the sampling distribution of sigma square, the MLE estimate of sigma square, with n equals 10, n equals 100, and n equals 1000, that should be 1000, and compare this to the bias corrected sample variance as described in slide 9. And we'll just look at it in table. This is the summaries of the sampling distributions we obtained. So we have MLE estimate for n equals 10, MLE estimate for n equals 100, MLE estimate for when the sample size is 1000, and a bias corrected estimate where the sample size is 10. This gives us the mean value of our sampling distribution, its variance, and its mean squared error. And so what we can see is the MLE estimated is biased, okay? When n equals 10, the mean of the sampling distribution is 3.666, and in fact the theoretical bias should be equal to minus 0.4, so we see that coming through in these very small sample sizes. The bias corrected estimator is unbiased, and this is demonstrated by the fact that the MSE and the variance are equivalent, essentially, as they should be for an unbiased estimator. Now note that although the MLE estimator is biased, and you can see that in the difference between the MSE and the variance, it is consistent. And this is evident from the fact that as n increases in size, the theoretical bias, sorry, the formula, as it's evident from the formula of theoretical bias, but it's also evident from the fact that the results tend towards the true parameter as n increases. So although the bias corrected estimator is unbiased, it actually has higher mean squared error than the maximum likelihood estimator for the same n. We can see that here. And this is because it has higher variance in this case. So MLE estimator is consistent but biased. The bias corrected estimator is biased but actually has higher variance than MLE for small sample sizes.